Okay, there are the contributors for this project. I already got it. Yeah, to screen. Nothing.
You have to push on the screen there. It's another mouse.
Yeah, and also for the funding part, thanks for the funding part for this following project. Before the start, I would like to say thanks once more to Interpol and ProLab to give me this award and have this chance to stand here. And I also go to the Interpol 2022 to get this award in person. Amazing. Thank you. So my research work mainly about the interface transport, and it's generally transport. It's all the interface. So it includes the fluid-solid reactive transport and the ion exchange, also the fluid displacement, and also some work about heat and mass transfer in the porous media. So for the applications, they are this list, and also some pure scientific problems. For the method, I used both numerical and the experimental one. For this block is a experimental method I used, and there's a experimental one. So the project I'm focusing is the CO2 storage and the radio works. Okay, so the main word about this topic I would like to say is the heterogeneity. As we know, for the porous media from the nature, they always heterogeneous, and how can we characterize the heterogeneity and how the heterogeneity affect the hydrodynamic properties of the porous media. So the first thing is how can we get the image? We're using the SEM, DEM, this kind of technology to get this 2D high resolution image is one way, and also usually we use the macro CT or the medical CT to get a larger view. But the challenge is that how can we get the larger view with the high resolution? It's quite challenging now. So here, to focus on this challenge, we propose the method based on the machine learning method, and it's includes the FastGAN and the CycleGAN. And the FastGAN is just proposed, I think, 2 or 3 years ago to generate the numerically generate a lot of image based on the input, and also use the CycleGAN to construct the relation between the high resolution and the low resolution image. Here's one thing I would like to point out is that for this kind of model is unpaired. We don't need this one is paired. You can see it's just the same location, same high resolution or low resolution, but here is the unpaired. It's just construct the relation between the low resolution and high resolution. And then we construct these 2 samples for the shell or shell reservoir. It's quite heterogeneous. And you can see here after the enhancement, we can clearly see the mineral or the topology heterogeneous for this one. And also for the comparison, we also interpretation for this model, the same size, but you can clearly see for the boundaries much higher with the enhancement one. Okay, another way we can get the heterogeneous model is we extract the network from the image, the city image. But it's always challenging because we cannot guarantee it's as large as possible to include the location correlation, this kind of information. So we propose a method to generate the networks with the heterogeneous. For this one, we generated the correlated field and generated the topology, and then we map the topology to the pore radius field and allocate the pore-size to the topology part. So finally, we can construct the correlated model, the heterogeneous one. And for this 3, this is uncorrelated and this is high correlated. And you can see this is the pore-size and the pseudo-size distribution. They have the same distribution. All of them are the same pattern for the log normal, but the location is different. Also, we use the same variation to evaluate the correlation lines. Another multi-scale network is the manual heterogeneous. So for this one, we use the medical CT to scan it, and get for different locations, we get to we do the segmentation, and then for each part, we do a macro CT scan and get the statistical information, and then generate them and connect them. It's another approach to realize it. Okay, after we get the model, so we did the hydrodynamic simulation, and the first is the absolute permeability and the interior capillary pressure. So for the correlation, we can increase as much as we want, but is the realization REV, we should guarantee it before we do the simulations. So from this one, we did the 10 realizations, and until here, after we think the variation is not acceptable. So the conclusion is that to investigate the heterogeneous, the smallest sample dimension need to be at least 20 times larger than the correlation lines. Okay, so that's the limitation we investigated for the following research. Using the generated network, the first thing we investigate is the transition from the viscous fingering to capillary fingering, and its application of GPU-based fully implicit dynamic for network modeling. You can see for this one, this is the capillary fingering, and this is viscous fingering, and there is a transition part from this one. And the conclusion for this project is the residual saturation at the breakthrough point has a non-Newtonian behavior with the increase of the capillary number. And there are the reactive equations for this for implicit for network models, and there are the local rules about the interior capillary pressure and the capillary pressure relation. This one, and
this is what you're doing in the dynamic network.
Yeah, exactly. And also the snap of when the pressure of the Solute is smaller than this one. And also this is a numerical model we construct. There are the residual equations for each phase. This is the two pressure system for networks. And this is the total residual saturation. We construct the matrix, and we using the Newton-Raphson method to iteratively solve it. And here we use the fully implicit, so the time step can be larger. And also we use the GPU accelerated, so the calculation is much faster than the formal work.
Okay. So there's saturation in each link.
Yeah, exactly.
Right. And that's basically what you're obtaining.
Exactly.
And then you have a relation with the
saturation and capillary pressure.
Yes,
Yeah.
as you call it. Okay.
Yeah. For this model, before we do that, we also did one validation with the experiment. This one is from one of my colleague Hamid, and we compared with them for two flow rate, and you can see both the time and the space distribution are comparable. Another thing we did, we have the process correlation affect the Solute transport, and it's the application of the GPU-based two-phase flow. It's the quadratic one. It's not the dynamic one, because for the dynamic one, this one is too computational cost. We cannot realize it as large as we want, because we would like to investigate the heterogeneity effect. So for this one, each point we can use less than 1 minute to realize the calculation. So we can calculate as much saturation as possible. For this algorithm, we do the two-phase flow to reach a saturation, and at specific saturation, we keep the inlet concentration in 1 and see half the Solute transport in the pulse media. So this is the velocity field. We give it a threshold to separate the stagnant, no flow part, or very small flow part, and the flow part. So for each of them, we have here I plot the average concentration at the 0.2 and 0.6. Yeah, we can clearly see that there is a correlation between the stagnant and the concentration field. Also, we quantitatively analyzed how the concentration change with time in the whole domain. This is the total concentration. It's a clearly non-Newtonian, non-thickened behavior. And for the flowing region, it's thickened. Yeah, the red part of this one is the flowing region. It's the thickened performance. And
how do you see that?
Sorry.
I mean that it's non-thickened.
Because for this one, you can see this is not perfect S curve. This area is not.
Okay, so the definition would then be error function or something like that?
Yeah,
Yeah, okay.
Yeah.
Mm.
and yeah, it is the error function we iterate. Yeah.
Yeah.
And this is for the stagnant part, definitely it's the non-Newtonian clearly before performance. And this is for the outlet. Yeah, this is not my leading work. It's from my PhD by Senyou An and another colleague Senyou. And this one is the same algorithm with the simulation. We did the single train for the experiment for this one. Displace it to one saturation and add saturation to the Solute transport and see how the Solute transport locally and mixing the advection diffusion in the porous medium. Yeah, this one is led by Senyou An, Hamid, and Yongqiang. They did the loading, unloading to investigate how the Solute transport in the porous media. And the interesting conclusion is that the Solute transport during the unloading was much longer than the loading part. And from now, our explanation is dispersion coefficient it is much larger during the unloading process. Yeah. Yeah, another work I would like to introduce is about the non-Newtonian fluid. As we know, the non-Newtonian fluid, the viscosity of it is sensitive to the shear rate and sensitive to the temperature. So how the non-Newtonian fluid flow in the porous media? This is the model we describe the viscosity with the shear rate and temperature. This is called the modified meter model. This is from the TechShark. And the question we would like to answer for this project is how the process correlation and the fluid property affect the heat and mass transfer in the non-Newtonian fluid. The first is about the mass. Yeah, let's see this one. The mass transfer. The temperature is constant now. The mass transfer in the porous media because the viscosity is sensitive to the shear rate. So for the high flow rate part, it's have a low viscosity, but for the low region, it has a higher viscosity. For the Newtonian fluid, here I call it water. You can clearly see for the shape factor, it's the linear change. But for the this is one kind of non-Newtonian fluid. It's non-Newtonian behavior. For the low flow rate, this region, it has some performance of Newtonian behavior, and for the high flow rate, it also covers this one. But for this linear, this slope range, the variation, the sensitivity of viscosity is the highest to the shear rate. So we got the non-Newtonian behavior of the shape factor, the average concentration at the breakthrough point with the flow rate. So, and also it includes the heat transfer in the non-Newtonian fluid. This one is inject the fluid from the center with high temperature, but the sample is saturated by the fluid with low temperature. So how the temperature field spread is the porous media system. And we also can clearly see here, I said moving the fingering, and how about the front, how about the evolution of the temperature. And also we can get a very clear non-Newtonian behavior for this performance. There are the viscosity and temperature at the breakthrough point with the increase of the flow rate. And for the average temperature, we also can clearly see this one at around 0.75. This flow rate reaches this line, and then they come this direction and back here. Okay, all of these projects are finished during my PhD, and this is the project what I'm doing now. It's the pore-to-core linkage for CO2 storage. This is the project funded by Shell and the EPSRC, this one. So the whole idea for this one is to construct the model, the core scale model with the heterogeneous distribution of porosity, the capillary pressure, and also the absolute permeability, this kind of parameters. And if the sample is not large, it's for example, it's 6 centimeter, we can put it in the macro CT and scan it RUV by RUV part by part. We can get the image-based model, that's fine. And it just take a long time to visualize them. And for each RUV, we use the pore-scale, the core-scale model to get the parameters, and then do the simulation for the core-scale. It's reasonable. But if we would like to characterize a sample with larger size, this one, for example, around the 30 centimeter, we cannot use the microcity anymore. Yeah, we can do it, just cut it section by section, but we cannot do the flow anymore. So we use the medical city to do this part. So we first scan it for the dry scan, and then saturated by the wetting phase water, fully saturated by wet phase and scan it, and then saturated by the nitrogen, also one phase saturated to scan it, and then we displace it. It's the steady state using the different fractions. For example, 10% nitrogen, 90% of water, and inject them together to get the distribution and scan it to get the saturation. There are the equations to how to calculate the porosity, how to calculate the saturation distribution during this process. And then for this one, we do the image processing, and we add a lot of algorithm we should operate to align the image to do the RUV upscaling, and we can get the porosity distribution in the sample. It's from inlet to outlet. This is the average one. After we get the porosity distribution, we use the relative perm from high flow rate. It's the viscous dominant as the input, and also we modify the capillary pressure in each RUV, and we update the absolute permeability for each RUV based on the capillary pressure and the porosity. Then we compare the simulation with the experiment and iteratively solve it. Finally, we can match the simulation result with the experimental one. This is the validation. You can see this is the final fraction from inlet to outlet. The saturation have a higher correlation with the experimental one. And this one is also for point by point for each RUV. It also have a quite linear relation. The correlation for this one is around 0.95. So we think it's accurate enough. So to estimate whether our constructed model is correct or not, we do the low flow rate simulation, and we get the relative perm here, the dashed line, and compare with the experimental one. It's the cross point, this marks, and you can see they also have a very high correlation. So why we do this one? So what can we get from this algorithm compared with the experimental? From the experimental, we can get the porosity distribution. So how can we get the absolute permeability distribution? How can we get the capillary pressure curve distribution? This is the question we advanced here. So after this one, we get this kind of distribution. So the model is constructed, the information is enough for the larger scale simulation. If we put this information to the core scale simulation, and we change the flow rate to get the radial from or other informations, and this information can be utilized for the field scale simulation. Also, for core scale simulation, we did some experiment to investigate how this heterogeneity of the geometry and the capillary heterogeneity affect the trapping. This is when we did using the synchrotron, using the ESRF recently, and you can see here, when we inject the nitrogen, and there it cannot break through this one, and when it reaches a state, how it breaks through, how the capillary trapping happens during this area. This is what we investigate, and this is the team at the ESRF. Also, as I said, why we do the core scale one? So finally, we will use this core scale information for the field scale, and we would like to from the core scale to core scale, and then to the field scale upscaling, and utilize for the real onset investigation. This is how the field scale heterogeneity affect the CO2 injection. So when we inject the CO2 here, if it's homogeneous, it's just reach the top very quickly. But if it has some capillary heterogeneity, how the CO2 distribute in this reservoir. Okay, if you are interested, we can discuss more about this kind of project. I just quickly go through them and yeah. Okay, this is another project I did about the CO2 saturated brine inject to the pulse media, and with the time evolution, the CO2 saturated brine react with the solid phase, and the solid dissolve in the fluid part. And so we investigate how the pH, how the temperature, how these parameters affect the reaction and the evolution of the solid fluid interface. And another project I would like to quickly introduce is about the low salinity water flooding. It's the application of the two-phase lattice boson investigation. So the sample is saturated by the oil first, then we inject the high salinity water to displace it to reach the steady state. It cannot displace more. So then we inject the low salinity one. We can clearly see the wettability changing and more oil is displaced out. This is a 3D model, but for the macro model, I just cut the middle slice of the sample. And also, before we do this one, we also did the validation, how the bubble detached from the solid phase when it's surrounded by the low salinity water. And okay, this another one is the emulsion water. Is the experiment also we did some simulation. This is this experiment is conducted by Dr. Javad, and I collaborated for the image processing and also the computational one. Yeah, if you are interested about this one, we also can discuss it in detail. For this one, we also did the box scale, the tubal test, how to the emulsion generated and how it improves the recovery. Also, another one is the hydrate topology evolution during the decrease of the pressure. So we generate the hydrate in the pulse media, and when we decrease the pressure, have the saturation of the hydrate evolution during this process, how to recover it. Yeah, just a quick for each project, each slide. And this one is the numerical one. We generate the hydrate in the pulse media, and for different patterns, different saturations. So for each pattern, each saturation, we do the simulation for each state. And so we investigate how the hydrate pattern and hydrate saturation affect the hydrodynamic properties. Okay. The last but not least one is the biomedical application. This one is for the image processing. It's the level set image segmentation. These are to continually track the bleed vessel, how the shape of it, and also the blood flow in the human eye, the capillary layer. So we got the image from the donors, and then we do the segmentation, and we do the simulation to get the velocity, the pressure, and the wall shear stress distribution. So this is how the particle movement during the pulse media. So this one is the pulse media structure, and this is the velocity distribution. Okay. Yeah, it's a quick talk. Thank you very much, and for all these contributors for this Alista project, and also for thanks for Lab for this support. Yeah, yeah.
Could you go back to the one before?